Hi everyone. Again discussing introductory topics today. In this section we will focus on roots, or what we often call radicals. Radicals can be symbolized by the root symbol that you've probably seen in the past, or expressed as a fractional exponent. More specifically, taking the nth root of a is equivalent to writing a to the power 1 over n. Right from the onset, let's note that radicals are functions, and therefore, as we'll see when we talk about functions later on, there is at most one result that can be obtained from rooting a number. Contrary to what many believe, the root of 4 does not produce two possible outcomes, notably 2 and minus 2, but only one, which is the 2 itself. So we're going to demystify a few rules regarding the roots in this video. First of all, let's talk about the simpler case, which are the odd roots. So if n is an odd number, then the nth root of a is defined for all real numbers a. In other words, you can do the nth root of any number, whether it's positive, negative, or 0, when n is odd. The result of the nth root of a is equal to b if b to the n is equal to a. The sign of b will have to be the same as that of a. For example, the cube root of 8 is 2, since 2 to the power 3 is 8. The fifth root of minus 100,000 is minus 10, because minus 10 to the power 5 reproduces minus 100,000. When it comes to even roots, we have to be much more careful. If n is an even number, then the nth root of a is only defined for non-negative numbers. In other words, a has to be 0 or positive. The result of the nth root of a is equal to the positive number b, such that b to the n equals a. For example, the square root of 25 is 5, because 5 is the positive number that you can square to get 25 with. The fourth root of 16 is 2, because 2 is the positive number for which 2 to the power 4 is 16. And the sixth root of minus 1 is simply undefined, because the argument minus 1 is negative. It's a misconception to think that rooting x squared will result in x, because there's no guarantee a priori that x is a positive number. For example, yes, it is fine to assume that rooting 5 to the power 2 will produce an answer equal to 5. The outcome in this case is a positive number. So 5, which is the x value we used from the start, squared and then rooted, ended up reproducing the same x equal 5 by the time we did our computations. However, observe how it's false to assume that minus 3 squared followed by a root will equal minus 3, because this time minus 3 is not a positive outcome, which it should be. The correct result should actually be plus 3. Minus 3 squared equals 9. Rooting 9 has to give the positive outcome that squared would have given 9 in the first place. So this time, if we think of minus 3 as being x, the result is not the same x, but one that has changed signs. In fact, minus 3 has become minus 3, or plus 3. Which leads us to the other misconception, which is to think that rooting x squared will give plus or minus x. Once again, the outcome has to be positive, and we're never sure, or we're definitely sure that from the list plus or minus x, one of them is negative. Again, two outcomes are not allowed here. So this would wrongly imply that there are two distinct results to the root, and instead we should always write that the root of x squared reduces to the absolute value of x. This way we're absolutely sure that the outcome is a positive one. Equivalently, we could write that square rooting x squared equals x in all cases where x is non-negative, whereas square rooting x squared is minus x for all cases where x was negative. Don't be misled by the signs. If x is a negative value, minus x will be a positive outcome as it should be. Radicals, or roots, obey for the most part the same properties as exponents. In fact, radicals are symbols that are used interchangeably with exponents. The nth root of a, as we said earlier, is equivalent to a to the 1 over n. So here are properties of roots that can be applied. The nth root of a product of two numbers can be split up into the nth root of each individual number, since this property would be true about exponents. The nth root of a quotient can be distributed to the individual terms of the quotient itself. Again, this is a property that was true for exponents and therefore is true about roots as well. If you are rooting a power, then you can interchange the order of the power or the root. This too comes from the property of exponents on consecutive exponents. So having a to the m to the power 1 over n is equivalent to rooting a to the m, and having a to the 1 over n to the m is equivalent to rooting a followed by a power. These properties can be applied as long as all operations along the way are well defined. Okay, so you have to be careful about when to apply them. For instance, 100 is equal to minus 4 times minus 25, but in such a case we would not be allowed to split the roots because root of minus 4 and root of minus 25 are not defined individually. Properties can be used to simplify radical expressions. For instance, 800 rooted, or the square root of 800, can be thought of as 400 times 2 being rooted. Now, why did I pick 400 rather than, for instance, 200 times 4? It's simply because 400 is the biggest number I could think of that turns out to be a perfect square. So root of 400 times 2 can be split into root of 400, root of 2, and root of 400 is 20, 20 being the positive number that is the result of the root of 400. Cube root of 64 over 125. So here we're going to use the property that allows us to apply the cube root to each, to the numerator and denominator individually. The cube root of 64 is 4 because 4 cubed is 64, and the cube root of 125 is 5, so we have a reduced fraction. In this case, we are doing the fifth root of minus 32 over 3,125 all squared. Notice how the operation I've selected here is to interchange the order in which the operations are done. Rather than squaring minus 32 over 3125 and then proceeding with the fifth root, I'm going to find the fifth root of the fraction and then square. So rather than making the numbers larger by squaring them, I'm going to start by making them more manageable before squaring them. Now, the fifth root of the fraction can be applied to the individual terms of the fraction. So the fifth root of minus 32 and the fifth root of 3125. So on the numerator, minus 2 is the outcome. On the bottom, the fifth root of 3,125 is 5. And then we have just to square the result. So we're squaring the minus 2 as well as the 5 to get 4/25. Same idea, we're going to simplify the expression that involves variables in this case. So the root of 25x squared times y to the power 4. I say root, I guess I should say the square root. All right, so we have a product. And please do observe that in this product, every single term is positive. 25 is a positive number. X squared is definitely positive, and so is y to the power 4. And therefore, it would be completely legal to root each term individually. All of these are well defined. The square root of 25 is 5. The square root of x squared is the absolute value of x. So here's where we have to be careful. We don't know if x represents a positive or a negative number, so we place absolute values on the x to guarantee a positive outcome. The square root of y to the power 4 is y squared. This time, no need for absolute values, because the fact that y is squared guarantees this is a positive outcome.